So today we're going to be working on problem 2 from the fall 2015 midterm, and we have to calculate the input impedance, your gamma in, and the VSWR in a 25 ohm transmission line when the circuit is shown below, and the frequency of operation is 1.59 gigahertz, and the system impedance is 50 ohms. So the first thing we have to do is pretty much like simplify the circuit. So we're going to start on our right hand side, and we're going to combine our ZL and our resistor here, and since they're in parallel, we have to find the admittance of them to add them up, and the admittance is just 1 over your impedance. So Y is your admittance, which is 1 over your impedance. So for our ZL, we'll call it, our admittance would be YL equals 1 over ZL, which is 1 over what we're given, which is 40 plus 75 J75, and this is in complex form, but in order to divide, we have to put it in polar form. So in order to do so, it's going to be the square root of 40 squared plus 75 squared, which is 85, and tan inverse of 75 over 40, which is 61.9 degrees. So that is 1 over 85 and 61.9 degrees. So now when we divide, we're going to be dividing the magnitudes and subtracting the degrees. So 1 over 85 equals 0.0117, and 0 minus 61.9 degrees is negative 61.9 degrees. And we have to convert it back into complex form in order to add it with this impedance. So in order to convert it back to complex form, it's going to be, for our real part, it's going to be our magnitude, which is 0.0117 times cosine of our angle, which is negative 61.9 degrees. And for our imaginary part, it's going to be J times the magnitude of sine negative 61.9 degrees. And we get 0.0055 for a real part, and negative J 0.0104. So 0.0055 minus J 0.0104. And our admittance of our resistor, we'll call that Y1, is I'll just add them together to make it easier. So our Y1 is going to be our equivalent admittance, which would be YL plus the admittance of our resistor, which is 1 over the impedance, so 1 over 75. And this is going to give us a real number, so we're going to be adding it to this. So that gives us 0.0189 minus J 0.0104. And since we are going to combine this and this, it's going to be in series with the inductor. So if it's in series, we just do normal addition. So we can convert that into imaginary, polar. So like we did over here, it's just going to be square root of 0.0189 squared plus negative 0.0104 squared, which is going to give us 0.0215. And for our angle, it's going to be tan inverse negative 0.0104 over 0.0189 and give us negative 28.8 degrees. And this is still an admittance. And if we want to add the inductor in series with the equivalent of these two, we have to convert it into impedance. So since admittance is y equals 1 over impedance, we get impedance equals 1 over admittance. So we can do 1 over 0.0215 and like 28.8 degrees. Again, we're going to divide the magnitudes and subtract the angles. We get 46.4 and 28.8 degrees. So now we can convert it into complex form, similar to what we did over here. So we would get 40.7 plus J 42.4. And since we're going to add the inductor in series with this, we'll call it Z2 equals Z1 plus J omega L, because that J omega L is the impedance of an inductor. And we can calculate our omega using the formula 2 pi times F, which is a frequency. And that would give us omega to be 10 to the 10. So when we add them together, we would get 40.7 plus J 42. Actually, this should be 22. 22.4 plus J times omega, which is 10 to the 10, times our inductor value, which is 2 nanohenries, which is 2 times 10 to the negative 9. And that would give us 40.7 plus J 42.4 for our Z2. And now we have the equivalent impedance of these three. So we can use whatever we got over here, which we just calculated, to add it to the impedance of the transmission line of length 0.1 lambda. So for that, we'll call that, since it's in series, we're just going to add impedance and not admittance. So we give that Z3. We're going to use the formula Z0 of times Z2 plus J Z0 tangent beta L over Z0 plus J Z2 tangent beta L. We know our Z2, which is this, and we know our Z0, which is 25 degrees. We can calculate, we don't know our beta L, so we can calculate beta L because beta equals 2 pi over lambda, and our L, as we said, is 0.1 lambda. So lambdas cancel out, so we get 0.6283 radians, but we want to convert it into degrees because we want to find the tangent of that angle. So to convert to degrees, it's just going to be 180 over pi times 0.6283, simply gives us 36. So Z naught Z2 plus J times 25 tangent of 36 degrees over Z naught plus J, or 25 Z2 tangent of 36, and there should be 36 degrees, and this should be 25. So you pretty much just plug in your Z2 over here and over here, and then after you calculate everything, you would get 42.8 minus J 42.8, which is 60.5 and negative 45 degrees. So now we have to we have everything up until this point. Now we have to take into consideration this stub transmission line. So the formula for that is Z stub equals J Z naught tangent beta L. And using the same formula we used over here to calculate beta L, it's going to be 2 pi over lambda. In this case it's 0.2 L because, 0.2 lambda, because that's what we're given here. It's going to give us 72 degrees. So plugging into the equation, you have J, Z naught is 25, should be 100, because given Z naught to be 100, tangent of 72 degrees, which will give us J 308. And since this is in parallel with the equivalent with resistance or impedance we've calculated earlier, over here we have to convert this into admittance. So Y stub equals 1 over Z stub, and this gives us negative 0.0032. So, like I said, since they're in parallel, we have to convert our Z3 into admittance as well. So it's going to be Y3 equals 1 over Z3, which is 0.0165, 45 degrees, which equals 0.0117 plus J, 0.0117. And since both of them are in admittance, we can just simply add them together like normal. So Y3 plus Y stub equals 0.0117 plus J 0.0117 minus J 0.0032, which gives us 0.0117 plus J 0.0084. And since we want the input at impedance as stated in the question, it's going to be 1 over Y in is Z in, which is 69.4 negative 35.8 degrees, which is equal to 56.3 minus J 40.67 ohms, and that's our Z in. So next we can calculate our gamma in. So our gamma in is just our input impedance minus Z out or Z naught of the system over Z in plus Z naught of the system, and that's just 56.3 minus J 40.67, and our system impedance is 50 ohms because it says that in the question, and 56.3 minus J 40.67 plus 50, and it gives us, it's there, and when we divide everything, you would get 0.361 and negative 60.3 degrees. And to calculate the Vswr, we need the magnitude of our gamma, we'll call it gamma 2, which is this gamma. So gamma 2 equals Z2 minus Z naught over Z2 plus Z naught. And this Z naught is the Z naught of our transmission line. So that is just 40.7 plus J 42.4 minus 25 over 40.7 plus J 42.4 plus 25. And when you divide that and simplify, you get 0.578 and negative 36.8 degrees. And for VSWR is 1 plus rho over 1 minus rho, and the rho is our magnitude of gamma 2, so it's 1 plus negative 0.578 over 1 minus negative 0.578, so you get 3.74. Or actually, there's no negative sign there, so it's just 1.578, which is 1 plus 0.578 and or 1 minus 0.578.